Let's take a look at finding the electric field at this point P. I have a -3 microcoulomb charge here, and I have a 4 microcoulomb charge here. And I have these various distances here. This is, say, if you think about that as an x-axis or some axis, this is at 0 meters, and that's a 1/4 of a meter later. And then I'm trying to find it here off of it. So it is a two-dimensional problem. I do know the direction of the electric fields. So I do know the direction of the electric fields, that the electric field is going towards this. So at that point right here, that electric field is going this way. I'm going to call this 1 and call this 2. So this is the electric field from 1. It's going down towards that one, and it's going away from there. The electric field from 2. So this should be the electric field from 1 plus the electric field from 2. I guess technically at point P. So we need to first find the magnitude, and then we worry about the direction. So the magnitude of this electric field, I know the electric field is equal to kq over r squared, r hat. The r hat's a directional thing. I already thought through the directions, so I don't have to worry about that too much. So this is 9 times 10 to the 9th. Let's go ahead and take that next step here. 8.99 times 10 to the 9th is the Coulomb's constant or electrostatic constant. The charge that's creating this electric field is -3. I don't need to worry about the minus sign because it has an impact on direction, and I already know what the direction is. 3 times 10 to the -6th divided by that distance there. Well, I know this is 0.06 and this is 0.1. And so Pythagorean theorem, so this is 0.116619. Actually, I care about what r squared is. So let me go back to that one. So this is 0.0136. I don't need to square it again. That is r squared. That's r. That's r squared. 198. So 1, 2, 3, 1, 2, 3. So 1.983 meganewtons per coulomb. That's 1,000,000 newtons per coulomb. Probably could have done better in choosing my numbers. If I had made that picocoulombs, that probably would have worked out much nicer. And then from here, the magnitude, it's going to be, well, it's much farther away. So this distance right here is 0.25 minus 0.06 or 0.19 meters. So r squared is 0.0461, but the actual distance is 0.2147. It's farther away. This is bigger, but that's also larger, and it ends up causing something weaker. So this is from 1, the electric field at point P from 2 is going to be, I get 0.780 meganewtons per coulomb. Now these are the magnitudes here. I need to be able to add them together by breaking them up. So I need to figure out what that angle is there. Actually, I don't have to do it because we're dealing with the triangle created breaking this vector up is directly proportional to the physical triangle of the distances. And so it doesn't really, I don't have to find sine and cosine. That's an intermediate step, or I could just do proportional triangles. So I have my E1 here, the 1.983 meganewtons per coulomb. That is a similar triangle to the physical triangle where this is 0.1, this is 0.06, and this was 0.116619. And I need to figure out that and that. Well, that is to that as this is to this, and here is to here. Or, in essence, we are deriving the trig relationships here. I don't have to know the exact angle, but let's go ahead and do that. So that divided by that. So I have 1.983 over 0.116619 is, I'll call this A and B. So that is that as A is to 0.06. So if I do that division times 0.06, I get A. So 1.983, 0.116619 divided by 0.06 times. And so A is 1.020. mega newtons per coulomb. And B is, well, just instead of multiplying by 0.06, you multiply by 0.1, so 1.700 mega newtons per coulomb. Now, if I'd gone through and found the angle, and I could have done that, this angle right here, we'll cleverly call it theta. So I know that since these are two numbers that are given and this has a rounding in it, I'm going to do an arctan. So this theta would be the arctan of 0.1 over 0.06. So 0.1, 0.06 divided by arctan. And so the angle is a 59.04 degree angle. And so A would then be 1.983 times the cosine of theta. So if I did cosine, then 1.983 times, I end up with 1.020. And then B, 1.983 times the sine of that angle. And so 59.04 sine 1.983 times, and I get 1.700. So you get to the exact same place. Depends on if you want to use trig or use geometry. Like there's really a distinction between the two. I'm going to do the same thing with the other one. I know that I have my two triangles here. I have the physical triangle, and then I have the electric field triangle. The magnitude was 0.780. This was 0.19. This was 0.1. And this was 0.2147. And so 0.78, 0.2147 divided by 0.1 times. And so this is 0.3634. And this would be 0.6903. Taking this out one more decimal place than those, so I probably should round off, so I'll just go ahead and round off here. Now I am dealing with my electric field. I know the electric field at point P. This is written at the top of the other page. The electric field at point P from 1 plus the electric field at point P from 2. The electric field at point P from 1 is this one right here. This was going down and to the left. If I establish my IJ coordinate system in the same brainwash manner that I usually do, then this will be negative 1.020 I hat minus 1.700 J hat. EP 2 is going off in that direction, going that way. And so plus is going to the left, so negative 0.690 I hat plus, because I'm going up, 0.363 J hat. Adding these together, negative 1.71 I hat, and then here minus 1.337 J hat. And don't forget units. Units are critically important here, so don't forget units, mega newtons per coulomb, or I could 1.710 mega newtons per coulomb I hat minus 1.337 mega newtons per coulomb J hat. If you're going to put it on the outside here, make sure there are parentheses. Otherwise, you're just associating those units with the second term and not with the first term. So you need parentheses here, or you need to distribute it. From a slightly other point of view, this is pointing down into the third quadrant. Let's see if that makes sense. Because I had a positive charge here, I had a negative charge here. I expect my electric field lines to go from positive to negative. Again, think of this as a water fountain and this as a drain. It's going to go something like this. So basically anything over here should be pointing into the second quadrant. Anything over here should be pointing into, at least on this side, in this range right here, I'd expect anything to be actually traveling into the third quadrant, which is ours is. Anything in this region right here, I would expect to be pointing to the third quadrant. Anything here, second quadrant. And then over here, you got first quadrant stuff, second quadrant stuff, first quadrant stuff. That would be fourth quadrant. Actually, it depends on where you are in here. There's going to be some point where the transitions when you get out to the extremes. But the lab there is a lab that you're going to do that if you have trouble on that lab, then I know that you have not watched this video. So please make sure you're paying attention.